different. This is FCC's frequency allocation, and you can see, especially in some of the lower in the sub 6 gigahertz band, how occupied it is and how busy it is. Now, there are two options you can think about now. If as the use of wireless spectrum becomes increasingly congested or competingly required, you can either find the new spectrum, which is there's a lot of work being done in that domain. That's why terahertz and other spectrum where it's still unlicensed, there's no license and there's huge bandwidths available. But obviously the challenges along with it comes, right? So which is poor propagation, shorter distances compared to say sub 6 gigahertz spectrum. But that's definitely an option, and that's also an area where machine learning can help, but in a different way. The second option is, there's a lot of usage on these things are licensed or unlicensed, and there's a lot of usages, but it's still not intruder or somebody else trying to access spectrum in an unauthorized manner. So then comes the big question. Can we answer all these questions in an efficient manner? So probably, and we'll see, maybe there's a way to answer more than just one. Currently a lot of the work is, okay, I want to classify the modulation. How do I do it best? Now is where the talk begins, right? So multitask learning has been utilized in different domains, including natural language processing, to look at emotions and things like that. Now, can you use the same techniques now to build a single model that's small enough that can be compressed, where it can do multiple tasks? It classifies modulation, classifies protocol, maybe even classifies RF finger, customized so that they can be lightweight enough to be deployed on an edge network. So this slide is pretty much trying to give you the history or the story behind AI. And this is a pretty classic diagram that you have seen in different spaces. I've just started the inception of AI at where Frank Rosenblatt invented perceptron, but that's, ABM, right? We have already seen two winters obstacles that are faced. There was another dip, right? But now, as we are getting close to 2020, there's a huge explosive growth in AI. The question is whether this explosive growth is the truth and it's positive, or is it still a hype? Based on the information I have, or based on what I've seen in the market, I'm leaning towards that a lot of this is actually truth, right? Reasoning being, even if you pull up your Netflix, you pull up, what is it running? It's learning or AI-based solutions, models that are taking inputs from you, which is your data set, and your choices that you make, and trying to update the model to give you better results. There's also phase recognition. There are generative models that's trying to map one domain to the other. So there are many applications that have already been put into commercial use. So it's definitely not all hype. But the word of caution is, since AI has become the keyword here and the word that sells currently, there is a tendency to push AI into all the domains and to solve problems that may not be actually the core strength of AI, or may not, you may not require machine learning or AI to solve it, right? So that's where the danger is. But I'm optimistic at this point. But as time goes, obviously, as scientists, we will be evaluating, we'll see where we are, right? And I also wanted to state, machine learning is a subdivision of AI, or say it's a subset of AI in general, just to make that caveat point. But so overall, the takeaway is it seems reasonable and seems positive in terms of growth, but we'll find out what happens in the long run. But I'm giving this talk because I feel there's something at least positive, and there's something to look forward as a solution that AI provides. Now, why is, so we talk curves here, so you can see the data growth. It means how much your data that's being stored is growing. You can see the storage cost of data coming down, and then you can also see the processing power going up, right? So these are just different graphs showing that this might be what's feeding or what's led to the, again, AI coming out of its winter. So the main point, like I mentioned, is the computation, right? So computational resources have exploded or grown exponentially, and the use of GPUs and parallel processing has enabled us to actually deploy machine learning-based solutions much more adeptly. And that's one big reason why it seems to be different this time around. The computational power is there, and obviously as our needs increases, currently it seems promising. But at the same time, here's the word of caution from wireless point of view. Right? Though computation is available for most applications, right? You can have your big servers, you can have your cloud, but think about wireless. Think about your mobile devices. Think about your IoT devices. How many of them have a GPU on it yet? Currently, no, not much, right? So there's always still a constraint in terms of computational resources when it comes to wireless point of view. You might have an FPGA, those who know about FPGA, right? And the question is, can you deploy a machine learning model on FPGA? The quick answer is yes, but there are constraints, right? So even though computation has caught up, and that's something that is different this time, and it seems promising, but there's a word of caution in terms of wireless. Now, similarly, the second part is digital data, right? Now, compared to 10, 20 years ago, where even if you have a lot of data, there's hardly anything digitized. Right? But now, everything is digitized. Right? Cameras, anything that's captured, any videos, tons of videos on YouTube, all these data sets that are available for computer vision. So there is a huge advantage now because everything is digitized. So it is stored in clouds, it's available, you can train your models, and you can create even more digital data, and that's just growing, right? So that's going to be another advantage for machine learning. But again, thinking of digital data in terms of RF applications or wireless applications, it is still in its infancy. I don't want to say there aren't any. It is becoming more. It's increasing more and more. But at the same time, it is nowhere close to say ImageNet or the data sets used for computer vision or other programs, NLP. It's nowhere close to that, right? And these are not just cautions, but also pointers to you guys saying, we are open to contributions in these fields, right? Something. Unique data set that you create, a comprehensive data set that you create that becomes the state of the art for everyone to evaluate on, or solving this edge problem or implementing these machine learning solutions for edge might be your opportunity, might be a research topic for you guys, right? So, so there are positives, there are negatives, but I wanted to bring this into context of wireless communication or RF domain because that's where my talk is going to be. So, and with most of the slides, I will have at the end some of the sources and suggested reads, right, and pioneers in the field. So, for example, this is the overview. I would say this is a very limited overview of machine learning, right? It's broadly classified into supervised learning, unsupervised learning, and reinforcement learning. And personally, reinforcement learning, I think, is almost a completely another field and different from supervised learning and supervised learning. But according to tradition, it's still combined under machine learning. Right, for reinforcement learning, I would suggest reading Sutton's book, and for the deep learning or supervised learning, Ian Goodfellow's book referred here, deep learning is really good. From this particular picture and the perspective of machine learning in wireless, we have published a paper that's pretty popular now, machine learning for wireless communication and Internet of Things. You can access that. It's also put up in archive to get an understanding of how these things can be applied to machine learning, right? And similarly, there's another paper that we can look at, which is applying machine learning to UAV systems that I talked about earlier. So, so dividing these into three broad, right? What I'm going to focus on and what the shade in gray shows is I'm going to focus mostly on supervised learning and reinforcement learning. Now, when you think about supervised learning, right, several of the applications for supervised learning include RF signal classification, modulation classification, now implementing different signal detection techniques within MIMO in order to improve the MIMO system, help or improve performance. Similarly, in reinforcement learning, we have probably in wireless domain or in RF domain, it has been applied to dynamic spectrum access, intelligent power control. How do I control my power so that I'm not causing interference with others, but I'm maximizing the network throughput. Routing problems, so you're choosing which node to route to give you some of the gain. Cognitive radio, as being the secondary user, how do I intelligently access the spectrum as compared to the primary user? And obviously, overall, just radio resources allocation. This might be a multi-objective or multiple resource allocation problem, which means you have to choose frequency, power, modulation, etc. Right? So many decision-making problems, learning from the environment, really fits into the domain of reinforcement. So this is just an overview of just high-level machine learning and how these things are actually applied today for different wireless communication problems. And some of these, like I said, supervised learning and reinforcement learning, we'll be discussing in a little more details to give you guys motivation of how you guys can apply this to research that you might be interested in. Right, so now since we have seen a snapshot of the different machine learning techniques, let's bring in the focus of supervised learning and its application to the RF signal classification domain. So broadly, if you look at the works, right, before machine learning was used, this is probably the trend that you see. And starting with the traditional approaches, where machine learning was not exactly used, but there were feature-based approaches, maximum likelihood-based approaches, which were used to, say, classify modulation. And so you create time frequency transforms and about who is occupying the spectrum at that moment.